Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am one of the co-founders here, along with my younger brother, AJ Raj. As you can see today, I've prepared for us a new Algebra 2 lesson. We're almost to the end of our mini-series on logarithmic functions. Today, we're going to be doing our last lesson, and then in the next video, we'll be doing some practice problems just to help you out so you know what to expect on possible assessments. Let's focus on today's video, and that's going to be about translating logarithmic functions. So specifically, we're going to be shifting graphs of logarithmic functions vertically, horizontally, stretching, compressing them, etc., pretty much manipulating the graphs. And then we're going to be finding inverses. As you know, inverses of a function are pretty much the opposite of a function. So the input of a function is actually the output of its inverse, and the output of a function is the input of its inverse. So you're swapping the x-coordinates and the y-coordinates, essentially, when you're finding the inverse of a function. So today we're going to be doing two practice problems where we're going to establish understanding of how do we translate the parent function graphs of logarithmic functions, and then after that we'll be looking at three very short problems on how do we find inverses when we're given a log function. Before I get into the video, I would really appreciate it if you all could like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. Let's jump into the first problem. So this is problem number 5 in order of all the problems we've been going through in these log function lessons. In this problem, we're going to be translating the parent function, which is y equals log base b of x. We're going to be given base b, and then when we look at the translated function, we'll have an h factor and a k factor as well. And you'll see what I'm talking about, but it pretty much builds off of what we learned in the last lesson. So make sure to go check the last lesson out before watching this one. So here's the problem, and it's part A. We're going to have another part B problem. They're not related to each other in any way other than they both fall under the topic of we're translating a parent function. So in this part A, we're asked the question, how does the graph of y equals log base 4 of x minus 3, all that in parentheses, keep that in mind, that's very important, plus 4 on the outside, compared to the graph of the parent function. So how are we going to solve this? Well, I'll show you the solution pre-written, and then I'll walk through it with you. So here's all your work that you would do. As you can see, you'd set up XY tables, you determine domain, range, asymptotes, you determine properties of the translation, etc. Then you would actually graph it on a set of axes, and that's pretty much the problem. So let me walk through that again with you. First thing we're going to do is we're going to identify what the parent function is. So the parent function you can think of as like the parent of a family, in this case a function family. So a parent function in this case, parent function, if you look at the problem we've been given, y equals log base 4 of x minus 3 plus 4. So this minus 3 and plus 4, the translation, this is the minus h, and this is the plus k, if you remember from the previous video on translated log functions. So if we take those things out, we get that the parent function is actually y equals, or we can write it as log first. So it's pretty much log base 4 of x equals y. So we're pretty much taking out this minus 3 plus 4 factors. Those are the translations. If we just want the parent function without any translations, this is what we're going to get. And if we want to rewrite it in exponential form, we can do our little e, which goes like that. And this pretty much means that we're writing it as x equals 4 to the power y. That's the exponential way to write this log function. So that's the parent function. Now let's talk about the translation, which is what we've been given in this problem. So translation. Recall that pretty much the formula for a translation is log of some base b of x minus h plus k. I'm running out of room there, but that's plus k. If we want to rewrite the log that we've been given in this problem in the same format, we would write it as log base b. Instead of base b, we have base 4 of x minus 3 instead of x minus h plus 4. So that's what we've been given in this problem. what do we decipher from this translation? Well, whatever's in the parentheses is going to tell us how we're going to move along the x-axis. So how we're going to move horizontally. Are we going to move right? Are we going to move left? And by how many units? In this case, when we have a minus some number in the set of parentheses, we're actually moving to the right because h is positive, because we have x minus h. So if h is positive, then we get x minus 3 in this case. So h in this case is equal to 3. So that's why we get x minus 3, because the formula says we are doing x minus h. So it's almost the opposite. That being said, if h was negative, let's say we had negative 3 instead of positive 3 equal to h, then what's in the parentheses would be equal to x plus 3. It wouldn't be x minus 3. And in that case, we would move to the left if we had a plus sign in the parentheses. So we already know now that we're moving right 3 units. So I'm going to write that here, right 3 units. And then whatever's on the outside is your k. And k determines how you're going to move along the y-axis. So how you're going to move vertically. Are you going to move up, down, and by how many units? In this case, k is pretty straightforward. If k is a positive number, we're moving up. If k is a negative number, we're moving down. This case is positive, so we're moving up, and we're moving up by 4 units. So I'm going to write that as well. Up 4 units. So if we look at our parent function, we can use an xy table. We can determine xy coordinates. We can determine about 5, which is the safe number we always go with. If we want to use those coordinates and rewrite them as the coordinates of this translated log function, what we're pretty much going to do, given the information that right 3 units and let up 4 units, we're going to add 3 to our x coordinate, because of right 3 units, that's along the x-axis, so it's affecting the x coordinates, and then we're going to add 4 to our y coordinates. That's a lot that's the k factor, and k determines how you're moving along the y-axis, so that's going to affect all of our y coordinates. If you're a bit confused, I'll show you exactly what I mean, because right now what we're going to do is we're going to actually make the xy tables for the parent function, which in exponential form is x equals 4 to the power y. If I make an xy table like so, what I can do is I can pick 5 coordinates all centered around the origin, because this is a completely untranslated log function. So we could pick -2, -1, 0, 1, and 2, as I did in the last video, where we had the problem y equals log base 3 of x instead of 4. We're just picking the same number centered around the origin. What we do is we take these numbers and we plug them in for y, which is the exponent. As you can see, we're not doing what we usually do, which we pick x coordinates and we find corresponding y coordinates, because in this case we're working with inverses. So we're going to take these y coordinates and plug them in for y. 4 to the power of -2 is, remember, when you have a negative exponent, it becomes a fraction. So 4 to the second power is 16, but we have to put that in the denominator and we get 1/16. 4 to the power of -1 is just 4 to the power of 1 is 4, but we put that in the denominator, so we get 1/4. 4 to the power of 0 is equal to 1, as any number is that's raised to the power of 0. 4 to the power of 1 is 4, and then 4 to the power of 2 is 16. Okay, so we found the coordinates of the parent function. How do we find the coordinates of the new function? Because we want to compare these, and a factor of comparing is graphing. So if we want to find the coordinates of a new function, keep in mind what I said over here, where we're adding 3 to the x coordinate and adding 4 to the y coordinate. So if we apply that, we're going to add 3 to every x coordinate we see here, and we're going to add 4 to every y coordinate. So let's start with the x coordinates. 1/16 plus 3 is 3 and 1/16. That's a mixed number. 3 plus 1/4 is 3 and 1/4. 1 plus 3 is 4. 3 plus 4 is 7, and 16 plus 3 is 19. If we add 4 to each of these y coordinates, -2 plus 4 is 2, -1 plus 4 is 3, 0 plus 4 is 4, 1 plus 4 is 5, and 2 plus 4 is 7. So this is our new xy table for the new function. Let's now identify domain, range, and the asymptote. There's just one asymptote. Keep in mind, it's going to be a vertical asymptote, because exponential functions, which are the inverse of logs, have horizontal asymptotes, but the inverse, which is a log, has a vertical asymptote. So in this case, let's identify the domain of the new function. For domain, we're looking at x coordinates, and as you can see, as we go up the x coordinate list, we see we're getting to 3 and 1/4, then we're getting 3 and 1/16, so we're getting smaller and smaller fractions. As we get smaller and smaller, we're seeing that we're approaching 3, the number 3. At 3, there's actually an asymptote, so there's no value of the function there, and there's no value of the function to the left of x equals 3. Therefore, the domain continues from 3, but we're going to put that in a parentheses because there's an asymptote at 3, so we have no value at 3, but whatever point comes infinitely directly right to the point from the asymptote belongs to this function. So we have 3 all the way to positive infinity. As for the range, like we said, all log functions have an infinite range because we can just go straight up and down, as you'll see in the graph. And then the asymptote, as we just said, is at x equals 3. For the parent function, you can see that the domain is actually 0 to infinity because 1/4, 1/16, those are small fractions that approach 0, all the way to infinity. Range is also negative infinity to positive infinity, and the asymptote is at x equals 0, which is the y-axis. So we did our comparison. Now let's actually graph. And then give me a second to erase all this. Alright, so let's graph this translated function by using the xy table that we found. So it should be pretty straightforward. I'm just reading off of the xy table that we just came up with. First is a point 3 and 1/16, comma 2. So that's going to be over here at around 3, and we move up 2 units, so it's going to be about here. Our second point is 3 and 1/4, 3, so I'm going to move up here. Whoops, sorry for that. 3 and 1/4 up there. And then we're going to have the point 4, which is here. And then we're going to have the point 7, which is over here. I'm not going to graph the final point 19, 6 because, as you can see, the axis does not go up that far. So these are just going to be the 4 points we're going to work with. Then I'm going to just sketch my graph connecting these points. And that's going to continue downward, 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 and then just going to keep going. And then our asymptote we can represent with a hashed line. As we said before, it is x equals 3. So this graph will never cross that line. And that's it for this problem. So let's move on to the next problem. Again, we're translating y equals log base b of x. So we're just going to be in this problem graphing y equals log base 2 of x plus 2 minus 1. X plus 2 is in the parentheses. Just keep that in mind. So again, we're working with that same format of log base b of x minus h plus k. So I'm going to show you the work, how you get to your answer, and then that's all the work. And using those xy tables, you can draw the graph, you can sketch the graph of this log function. So let's do that working together. First, we're going to identify in any of these graphing problems where you see a translated log function, you always want to identify the parent function. In this case, the parent function, if we remove all that, if you want to think of it as like excess, you can get rid of this x plus 2 and then this negative 1 and just leave us with y equals log base 2 of x. So we're taking away this minus h factor and this plus k factor, which tell us how this is horizontally and vertically translated. We're just leaving the bare bones, which is the parent function. And if we want to rewrite this in exponential form, we can write it as x is equal to 2 to the power of y. Instead of y is equal to the power of 2x, we have x is equal to the power of 2y. Sorry, instead of saying y is equal to 2 to the power of x, we're saying x is equal to 2 to the power of y. I'm so sorry why I said it that way. But anyway, that's the parent function we're working with. If we want to look at the translated function, which is what we've been given in the problem and actually asked to graph and find translated function, I'm just going to rewrite it here as well. Y equals log base 2 of x plus 2 minus 1. And now that we have these written, we can find our we can make our xy tables. This will just make graphing easier. Because this is a parent function, again, we can find 5 points centered around the origin. So -2, -1, 0, 1, and 2. We just plug these in for y and find out what x is. 2 to the power of -2 is 1/4. 2 to the power of -1 is 1/2. 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. That was pretty straightforward. Now let's make an xy table here. And hopefully you can see what are we going to be adding or subtracting, or how are we going to be manipulating the points of the parent function to find the points of the translated function. So as you can see, in the parentheses we have x plus 2. when we have a positive number in the parentheses, that means h is actually negative. So if this was x minus 2, h would be equal to 2, because the formula is x minus h. But in this case, we have x plus 2. So h is actually equal to negative 2, because negative 2 times the negative sign already in the parentheses for the formula would give us a positive number. That's why we get plus 2 here. So h is actually negative 2, and then k is negative 1. So we're going to be subtracting 2 from the x coordinates and subtracting 1 from the y coordinates. So if we start, 1/4 minus 2 is equal to negative 1 and 3/4, mixed number. 1/2 minus 2 is equal to negative 1 and 1/2. 1 minus 2 is negative 1. 0 minus 2 is negative, so 1 minus 2 is equal to negative 1. 2 minus 2 is equal to 0, and 4 minus 2 is equal to 2. So now we can do the same thing with the y coordinates. If we look at the negative 1 we have here, we're just subtracting 1 from each of the y coordinates. Negative 2 minus 1 is negative 3. Negative 1 minus 1 is equal to negative 2. 0 minus 1 is negative 1. 1 minus 1 is 0. And 2 minus 1 is 1. So now let's just quickly identify the domain, range, and asymptote, as these things will help us with graphing. Asymptote. So the domain, as you can see here, it approaches negative, so you see we get to negative 1, and then we get into the fractions. So these fractions are getting smaller, these numbers are getting smaller and smaller, so you're going towards the left of the number line, if you want to think of it that way. But they never pass, like, negative 1, and you'll get some very, very large fraction. However, you're never going to get past negative 2. So that's why the domain goes from negative 2 all the way to the right, so to infinity. It'll never be equal to negative 2, because there's actually an asymptote, which I'm going to write here. There's actually an asymptote at x equals negative 2. It'll never go to left, and it'll never be equal to negative 2. And the range, as we say for all log functions, is negative infinity to positive infinity. So now let's graph this. So now let's graph this log function. I'm just going to use the xy table we just found. So our first point was negative 1 3/4. So negative 1 3/4 is over here. We come down 3 units and we're here. Then we have the point negative 1 and 1/2, negative 2. So we're going to come left 1.5 units and then come down 2 units. Third point is negative 1, negative 1, which is here. Fourth point is the origin, 0, 0 here, and the last point is 2, 1. So up here, this is a nice curve, so we can just sketch that. And then we can sketch the bottom part, hugging x is equal to negative 2, but never really touching it, just approaching it at infinity. And then we have our hashed line, our asymptote at x equals negative 2. And that's it for this problem. For our last problem, we're just going to be discussing how do we find inverses. We'll be looking at 3 really simple log functions and then finding the inverses of each of them. So the first one is y equals log base 6 of x, and in this case you can see there's no translations at all, so it's pretty straightforward. Remember, when we're finding an inverse, there are two steps you can think of. First, we are going to swap the positions of x and y. We're going to swap where they are, and then we're going to solve for y. So in this case, what we did was we actually took a step forward and we rewrote this in exponential form, just so it'd be easier for us. So if we rewrite this in exponential form, we get x is equal to 6 to the power of y. Then our next step is pretty much just swap the positions of x and y, and we get y equals 6 to the power x. So that's our final answer, because y is by itself, y is isolated. We don't need to do anything more to solve for y. Y is already solved for. As you can see, when you find an inverse of a log, you're going to end up with an exponential function where we have y on one side, then we have some number that's raised to the power x, and x is a variable we can plug in for. So just make sure that when you find inverses of log functions, you are finding exponential functions. Let's look at the second problem, which is a bit more challenging. Y equals log, and in parentheses, of x minus 2. Keep that in mind that we are in parentheses. That's going to be very important. So we can rewrite this as y equals log base 10 of x minus 2. Because this doesn't have any clear base, we can assume that's a common log, and common logs have base 10. So that's why we wrote base 10, and it's important to include that 10 because it will help you when you rewrite in exponential form. So if you rewrite this in exponential form, you're going to get 10 to the power of y is equal to x minus 2, which was in that set of parentheses. If you just do that squiggly e, you'll figure this out. Then what you want to do is you want to swap the positions of x and y. So in this case, we changed the exponent from y to x, and then we changed x minus 2 to y minus 2, and we got 10 to the power x equals y minus 2. Our final step to get y by itself is just add 2 to both sides, and we get y equals 10 to the power x plus 2. That's an exponential function, so we found the inverse correctly. And our last example is y equals log of x minus 2. It looks very similar to the previous problem, except we don't have parentheses, and you'll see what the lack of parentheses does and how it actually changes the answer. You can see that the answer here is different from the answer there, and you'll see that parentheses are very important in mathematical notation. In this case, our first step is going to be adding the 2 to the left side, so we get y plus 2 equals log x. Then what we're going to do is we're going to include that 10 because this is a common log since the base is not expressed. So we get y plus 2 is equal to log base 10 of x. Then we're going to rewrite this in exponential form. So 10 is raised to the power of y plus 2 because that was on the left side of the parentheses. So everything that's on the left side is going to be the exponent that 10 is raised to. That's going to be equal to x, and then our final step is just to swap the x and y, the position of x and y. We end up getting y equals 10 to the power of x plus 2. So x plus 2 is the expression, but that whole expression is the exponent, unlike in the previous problem where x was just the exponent and then the plus 2 was added afterward. So that's all about finding inverses. We'll do some more practice problems in the next video just so you get more comfortable with that. And that's all I have for you today. I hope you enjoyed the video, and if you did, please like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. Please also check out our website and Gmail. Thank you for watching, and I'll see you in the next video.